An angle is formed by two rays that have a common endpoint. One ray is called the initial side, and the other ray is called the terminal side. There's a rotation from the initial side. Theta is a measurement of rotation. So the shared endpoint, this point right here, of the two rays is called the vertex of the angle. When an angle is written in standard position, its vertex is at the origin of a rectangular coordinate system, and its initial side lies along the positive x-axis. The origin has to be where the vertex of the angle is, and the initial side of the angle has to be along the positive x-axis. This is a positive angle theta, and it's positive because the rotation is counterclockwise. So positive angles are generated by counterclockwise rotation. On the other hand, if you start with the initial side here, the positive x-axis, and you rotate clockwise instead, the angle that you create in standard position is going to be a negative angle. So negative angles are generated by clockwise rotation. All right. Now there are some special angles, and they're called quadrant angles. The first one I want to look at is 90 degrees. So we rotate a quarter turn, and when you do that quarter rotation, that's a 90-degree rotation. The terminal side of your angle will be along the positive y-axis. Whenever the terminal side of an angle lies along either the x or y-axis, the angle is called a quadrant angle. So 90 degrees, a quarter turn, is a quadrant angle. Another angle that's a quadrant angle is a 180-degree turn. So as you can see, a 180-degree turn is a half of a rotation. One half of a rotation. And a 180-degree turn, the terminal side is on the negative x-axis. So because the terminal side is on one of the axes, 180 degrees is a quadrant angle. This specific quadrant angle, the 180-degree angle, is called a straight angle. If we continue beyond that another quarter turn, so beyond 180 and we go to 270 degrees, so three-quarter turn, 3/4 of a full revolution. 270 degrees is a quadrant angle because the terminal side lies along the negative y-axis. So because the terminal side is on one of the axes, 270 degrees is a quadrant angle. And another quarter turn takes you to 360 degrees. One full revolution. So one full revolution, 360 degrees. The terminal side lies along the positive x-axis in the same place that the initial side does. So 360 degrees is a quadrant angle. But those aren't the only quadrant angles. They're not just positive. If you continue beyond 360 degrees, another 90 degrees, you'll get to 450 degrees, and that's another quadrant angle, and you can keep going. Or you can also go negative. If you go clockwise, negative 90 degrees, notice the terminal side is along the negative y-axis, so that's a quadrant angle, so it's negative 180 degrees. Half turn in the clockwise direction, so it's negative 270 degrees. Three-quarter turn, 3/4 of a revolution in the clockwise direction, or negative 360 degrees. So these degrees measure the amount of rotation. Negative 90 degrees is what we call a quadrant angle. All right. So degrees are not the only kind of measurements that we have for angles. We can also measure angles in what are called radians. So let's talk about radians. What is a radian? Well, given a circle with a radius of r, we're going to look at an arc along this circle by creating an angle. The angle we create is going to be centered, or is going to have its vertex at the center of a circle. A central angle of a circle is an angle whose vertex is the center of the circle. So this angle we've created, theta, is a central angle of this circle. And that central angle intercepts a part of the circle, this length right here. This little part of the curve of the circle is called an arc. That arc, let's call it S. So this little part of the circle here, this intercepted arc, has a central angle theta, and the circle itself has a radius of r. There's a relationship between the radius of the circle r, the intercepted arc length s, and the rotation theta. And the relationship is that theta in radians is equal to the arc length divided by the radius. So radians is literally a measurement of how many radiuses you can fit in that little arc right there of that central angle. So whatever arc the central angle produces, you're looking at how many times you can fit the radius into that arc. That's what a radian represents. So given a situation where you know the radius of the circle and the arc that is intercepted by that central angle, you can find the measure of the central angle in radians. Here's an example. So let's say we know that the radius of the circle is 4 and that the intercepted arc has a length of 5 inches. So the distance along this arc is 5 inches. Well, in that case, if you wanted to find the number of radians, or the radian measure of the angle down here, all you have to do is take the arc length s, which is 5, and divide it by the radius, which is 4, and you get that theta in radians is equal to 5/4, or 1.25 radians. So this angle, the rotation that's measured here, is 1.25 radians. All right, let's try another one. What if, instead of just taking a part of the arc, what if we take the entire circle? So what if the arc that we're going to look at is the entire circumference of the circle? So this is the circumference of the circle right here. The circumference of a circle is 2 times pi times the radius of the circle. If this is the arc, then I know that the angle here is 360 degrees. I want to know how many radians that is. How many radians is equal to 360 degrees? So the angle in degrees I know for a full revolution is 360. And now I'm looking at what the radian measure would be of 360. So I just take the arc length here, or the circumference of the circle, 2 pi r, and I divide it by the radius of the circle, which is r. So I get 2 pi r divided by r. The r's will cancel, and I'll just get 2 pi radians. So 360 degrees is the same thing as 2 pi radians. We are going to use that fact to convert from degrees to radians and from radians to degrees. Let's look at this example. So first, this is the fact that we're going to use. The fact that 2 pi radians, that's 1 full revolution, in the same way that 360 degrees is 1 full revolution. They both represent the same rotation. So let's convert 30 degrees into radians. Well, 30 degrees is only a fraction of the circle 360. So if I figure out what fraction of 360 30 represents, I can just find that fraction of 2 pi, and that will be the measurement in radians. It should be proportional. So first, I'll find out what fraction of 360 30 is by dividing 360 by 30. 360 divided by 30 is 1/12. So the angle, 30 degrees, represents 1/12 of a full revolution around a circle. The full revolution can either be called 360 degrees or 2 pi radians. Since I already know degrees, I'm just going to find out what 1/12 of 2 pi radians is. So I'm just going to multiply 1/12 by 2 pi. And that's going to be 2 pi over 12 or pi over 6 radians. So pi is like 3.14 divided by 6. So if you actually calculate this, you can get a decimal approximation for the number of radians here. All right, let's try another one. So we got that 30 degrees is equal to pi over 6 radians. Let's try to convert 156 degrees to radians. So we're doing the exact same thing here. First, we're going to figure out what fraction of the 360 degrees is represented by 156 degrees. I just find that fraction. It turns out that 156 over 360 is 39 over 90. So I just need to find out what 39/90th of 2 pi is now. I know that 156 is the fraction that's 39/90th of 360. That's the number there. I just need to find out what's 39/90th of 2 pi to figure out the radians. So I'm just going to take 39/90th and multiply by 2 pi. That's going to be 39 pi over 45 radians. So 156 degrees is 39 times pi divided by 45 radians. If you do this calculation, you can get a decimal approximation. A decimal approximation. All right. So let's try to go the other way. So instead of converting degrees to radians, let's convert radians to degrees. So what if we have 7 pi over 6 radians? We want to figure out how many degrees that is. Well, 2 pi radians is 1 full revolution. I want to figure out what fraction of that 7 pi over 6 represents. So I just find the fraction. 7 pi over 6 divided by 2 pi. To divide a fraction by a fraction, you keep the first fraction the same, and you multiply by the reciprocal of the second fraction. The reciprocal of 2 pi is 1 over 2 pi. So when you do this multiplication, 7 pi times 1 is 7 pi. 6 times 2 pi is 12 pi. The pi's will cancel and you'll get 7 over 12. So 7 over 12 is the fraction we need. That's the fraction of a full revolution represented by 7 pi over 6. I just need to know what degree measure that is. So I need to find out what's 7/12 of 360. So I multiply 7/12 by 360 degrees, and we get 210 degrees. So 210 degrees is the same as 7 pi over 6 radians. They represent the same amount of revolution, or the same amount of rotation, I should say. All right, let's look at coterminal angles. So let's look at this first angle, positive angle 120 degrees. That's not the only way of getting to this terminal side. The definition of coterminal angles is that two angles with the same initial and terminal sides but different rotations are called coterminal angles. So if I rotate clockwise instead, starting in the same place but rotating clockwise, I can create a negative angle that has the same initial and terminal side as the angle 120 degrees, namely negative 240 degrees. If I didn't see the actual rotation, I wouldn't know the difference between these two angles just based on initial and terminal side. These are coterminal angles. All right. What if also I start with the same initial side, so the angle is going to be in standard position. What if I rotate one full revolution, but then I go beyond that and I land on that exact same terminal side? So that angle is going to be more than 360. it's actually going to be 480 degrees. 480 degrees is bigger than one full revolution, more than 360 degrees, but it is coterminal to 120 degrees. There is a coterminal angle within one revolution. So 120 would be a positive coterminal angle that's less than 360 degrees for both A2 and A3. For both of these, this would be an angle that's both positive and less than 360 degrees, and it's also coterminal to these. Let's do the same thing. So here, find a positive angle less than 360 that is coterminal to the angle 528 degrees. So 528 is more than 360. Therefore, this is more than one full revolution. It's less than 620 though. So it's less than 2 full revolutions. All right, so what do we do here? Well, if I subtract 360 from this, I'm subtracting away the full revolution. So if I just keep subtracting 60 until I get a number that's between 0 and 360, I'll do exactly what they asked me to do. Turns out that if I subtract 360 just one time, I get the coterminal angle 168. And 168 is positive, so it's greater than 0, but it's also less than 360. This is the answer they're looking for. A positive angle less than 360 that's coterminal to 528. All right, let's do the same thing for this angle, negative 710. So negative 710, let's see. So first, since it's negative, subtracting won't help me here. In order to get this to be a positive angle that's less than 360, I have to add revolutions. So I have to add 360. So first I will add a 360. So add 360 to negative 710, and I get negative 350. Still negative. So I'm not done yet. I've only added one revolution, though I can keep adding revolutions until I get within the range of 0 to 360. So I'll just add another revolution. So if I add another 360 to negative 350, I'll get 10 degrees. 10 degrees is positive and less than 360 degrees. Therefore, 10 degrees is a positive angle that is less than 360 degrees and also coterminal to negative 710. All right, let's do the same thing now for an angle measured in radians. So this angle is measured in radians, and they want me to find a positive angle less than 2 pi that is coterminal to the angle given here in standard position. So less than 2 pi. 2 pi is 1 revolution, so they want a positive angle within the first revolution. This is not within the first revolution. 14 divided by 3 is like 4 2/3. It's way more than 2 pi. So it's like 4 and change pi. So I have to subtract away 2 pi's from this. I have to subtract away revolutions. So I'll subtract away 2 pi once. 14 pi over 3 minus 2 pi is 14 pi over 3 minus 6 pi over 3. 6 over 3 is 2. And now they have the same denominator. Now that I have common denominators, I can just subtract 14 pi minus 6 pi to get 8 pi over 3. Now 8 pi over 3 is still bigger than 2 pi, because 8 over 3 is like 2 2/3. So that's more than 2. So I still have to subtract more revolutions. So I'm going to subtract 1 more revolution because 8 over 3 is bigger than 2. And I need something less than 2 pi. So I subtract 2 pi again, but remember 2 pi is, or 6 pi over 3. And when I do that subtraction, I get 2 pi over 3. And 2 pi over 3 is a positive angle less than 2 pi that is coterminal to 14 pi over 3. So there I found the answer. All right. Next, we'll talk about angular speed, how fast something is rotating. So here's rotation. This rotation rotates through that angle in 2 seconds. Now, the angle that it rotated through was 5 pi over 4, and it took exactly 2 seconds to get there. So the angular speed is how fast it's rotating through an angle, just like how a linear speed is how fast something goes a certain distance. An angular speed is just telling how fast something is rotating. So in order to get an angular speed, you simply take the angle and divide it by the time. So angular speed, omega, this symbol is omega, angular speed is equal to the angle over the time. So in this case, since the angle is 5 pi over 4 and the time is 2 seconds, the angular speed here is 5 pi over 4 divided by 2. Once again, you keep the first fraction the same, you flip the 2 over into a 1 over 2, 1/2, and you multiply instead. When you multiply, you get 5 pi over 8. So 5 pi over 8 is the angular speed, or how fast this thing is going. Basically, it's doing 1.963 radians per second. 1.963 radians is a measure of how much rotation it does every second. All right, so that's the angular speed. There's also something called a linear speed. But let's calculate the angular speed of that. You see how fast that revolution was? That revolution happened really fast. It went the same distance, but it went there in only half of a second. Like by the time we saw it, it was already done. So this angular speed is different because it went the same distance, but it took less time. So this rotation was faster. The angular speed is a faster speed. So here we take the 5 pi over 4, which is the angle, and it did that 5 pi over 4 revolution in only a half a second. So we divide it by half. Once again, you keep the first fraction the same, flip the second one over and multiply. You get 5 pi over 4 times 2 over 1, which is 5 pi over 2. And 5 pi over 2 is approximately 7.854 radians per second. So you see, this is spinning faster. The first one was like 1.9 something. This one is 7.8 something. So it just shows the angular speed is spinning faster. Now, angular speed can translate into linear speed. Linear speed has to do with how fast a point is moving on an arc. So basically, if you have a radius and that radius is spinning through a certain arc, on that arc, there's actually a distance being traversed. If you take that green arc and stretch it out, you can visualize a linear speed, or the speed of the thing moving along this arc. This is like NASCAR. They're not moving in a straight line. They're moving around a circle. So if you're tracking the speed of the car, there's an angle that the car is creating with the center of the track, if it's a perfectly circle track. But there's also the speed at which the car is moving along the ground. That's called the linear speed. All you need to find the linear speed is an angular speed and a radius. The linear speed is equal to the angular speed multiplied by the radius. So here's an example. If you have a radius of 8 inches and it takes half of a second to move through an angle of 5 pi over 4, there's an actual distance that you travel in green here. And what we want to do is we want to calculate how fast you're traveling along that distance. That's the linear speed. So we're just going to take the angular speed, which we found by doing theta over the time, and we're going to multiply it by the radius, which is 8. So if there's a radius of 8, the linear speed along that arc, now that you have a radius, you just have to multiply that angular speed of 5 pi over 2 by the radius, and we get 20 pi. So the object that's moving along this green arc is moving at a speed of 20 pi inches per second. 20 pi inches per second. 20 pi is roughly 62.832 inches per second. That's how fast the thing is moving along that green arc.